At the mechanics, that would be great. That'd be cool. Like Holly Milton Bradley be like, do you want a game that 17? No, there's 350,000 people sit for the exam, so you know. So the idea is, if you're a buoy here on this current and you have a starting position. Nice. What's that starting position called in differential equation land? It's called, they name it. There's a certain term for it. Like if I picked that point as it's called something with an I, the initial what? Anybody know? It's called the initial condition, okay? The initial condition. You need an initial condition because the slope field represents all of the solutions to a particular rate. It's a particular differential equation, but it models how many different things could that model? Many. It's kind of like when I ask you the question, here's a derivative of something. What's the integral? How many integrals does a given differential have? An infinite number, right? You can always change the constant in one way to make another one. But the idea is once you have an initial condition, you can plot a course. Because at that moment, this slope field, if that's a buoy, it tells you where it's going next. And the instant it moves, you're at another point, and you can use the slope field to tell where it's going next, where it's going next, where it's going next. So what can you generate? You can kind of generate the entire equation. Something like that. The idea is the path going to change depending on where you're starting? Absolutely. Absolutely. Tell me a definition for a differential equation. It's you can par that down and use less words. It's an equation that has a
derivative at
a rate of change. That's literally what a differential equation is. A differential equation is an equation with a rate of change in it. That's what it is. Any equation with a rate of change is a differential equation. We use them. Why do we use differential equations in the first place? What's the point? Why don't we just start with the equation? Why do we start with the rate of change? We start with what we know. We start with the data we have. So we might know or suspect or have an equation for the rate of change first. We don't always have the equation for the position of the car. We might have the equation for what is its velocity going to be over time, and then an initial starting point. Then we can know where it's going. But sometimes we know the rate of change first. I really like these questions where it says, here is a differential equation. Which slope field does it match? Did you do any questions like this last year? Do you remember doing stuff like this? Okay, so do you remember some of the strategies you employed? Let's look at this differential. Here it is. If you put 3 in there, what happens?
Undefined.
It's undefined, right? So what is undefined visually represented by? Vertical line. So at anything, at 3, what about at 4, 5? So what should you see wherever x is equal to y? So literally you can just draw in y equals x and look at all of the points where it crosses. I know, I'm going to zoom in, don't worry. But over here, you see this right here? What do you notice? Where y equals x, the slope is what? Dy, this is dy dx is equal to what?
0.
Which is not what we want. Let's go to this one. What do we see? Well, the thing is you have to see the picture here. Are they all vertical? No, it looks like they're changing. But what about over here? Undefined. Dy dx is undefined. It's straight up and down. So usually, most of the time, you just need to check like 2 potential areas of investigation to figure out what it looks like. 2 potential areas of investigation to see. So for which positive values of p are the solutions increasing or decreasing? Matt, do you feel okay matching differential equations to their slope fields? What do you think about that?
Yeah.
Plot some points, match them. So we're going to jump ahead a little bit. I want to ask you a question to see what happens here. So on this question right here, this is a differential equation because it models a rate of change. Find me the relationship of y in terms of x. Yeah, okay, exactly, right. So you end up with, okay, dy is equal to e to the x squared dx, right? So what does that tell you? Y is equal to the integral of e to the x squared dx. So you can write it. You know that y is equal to that integral, but if you wanted to actually integrate that, you'd have to go through your lexicon. You flip through all the different methods you could try. And what happens?
No.
I don't know off the top of my head. But is that the solution? That is the solution. What did we do here? Does anybody know what this act is called right here? Separation of variables. Very good. Absolutely. On the AP exam, when they grade these, they will look for separation of variables. That'll be one of the points. If you don't get to the separation of variables part, usually that's the threshold for earning all the other points. Jesse and then Henry.
Why can't we use...
The thing is, we could try it. Now, if you want to try u substitution, you would want to try u is equal to what, Jesse?
X squared.
Sure. Okay. So we try u is equal to x squared. So that means du is equal... Yeah. What's du equal to? 2x dx, right? So dx is equal to du over what?
Okay.
2x. So you can do that, but what did you just throw into there?
2x.
Yeah, you end up with y is equal to this. You end up with e to the u times du over 2x, and all of a sudden you're stuck because you're in multivariable. But someone just figured out how we could do it. What could you use? Taylor series? Oh, Taylor series. Oh, we got a throwback question here. Look at this. We just combined slope fields, differential equations, and Taylor. What is e to the x? Oh, come on. As a class, can we remember this? Wait, what is it, Ray?
X plus x squared over 2 factorial
Yep.
plus x
Cubed over what? 3 factorial. It's the nice one, right?
Yes.
It's the nice one. So what is e to the x squared? X squared plus
X.
4th over 4 factorial plus x to the 6th over.
No.
Oh, it's 2 factorial. Thank you. Over what? Cool. So therefore, what is y going to be equal to? 1/3 x cubed, right? Plus x to the 5th over 5 times 2 factorial plus x to the 7th over 7 times 3 factorial, so forth. Sweet.
That's not the argument.
I'm not. Oh, absolutely. There are other methods. Hold on a second. Pause. Jesse, go ahead.